A request was made at the end of last class for another example question like this. So I did create one real quickly and turned it into a pseudo video. I didn't solve it. I just recorded it real quickly and posted it. So if you go into the modules for the course for week 13A, there's two videos there. Video 1 is how we went through and solved this one. Video 2, or B, is just the question with me mumbling some nonsense for about 30 seconds. Long enough to give you time to actually write down the question. And that's about it. Okay? So if you wanted practice that would give you kind of the whole spectrum, you've got more practice there. Okay? Which then takes us to the last kind of 2 bits of information that we would need before we can officially just do kind of whatever we want as study practice before the next exam. Okay? That first bit is looking at what is known as your empirical formula. We haven't really addressed the empirical formula concept because when we talk about our formulas or the compounds we're looking at, we're almost always looking at an ionic compound. And ionic compounds, by definition, are the reduced ratio. So if I looked at the compound for sodium chloride, the formula, what would I write? NaCl. Even though if I look at a larger structure, a sample of sodium chloride, there's probably billions of sodium atoms and billions of chloride atoms. Right? I still boil that down to the basic structure of NaCl. If I go through and do that for magnesium chloride, I get MgCl 2. I need 2 chlorides to balance that out. So the same idea, I boil that all the way down to the bare bone structures for that compound. And that's because as an ionic compound, we alternate those ions all the way out to the entire structure, very regular format, and we can predict all of that. Okay? What we haven't talked about is what happens when we look at a molecular compound. Okay? And so we could switch to something really simple like CO2. Be like, well, that's not a big deal. That's the reduced ratio. And we're right. Okay? The molecular compound, CO2, carbon dioxide, is a reduced ratio. It is in an empirical formula. But what if we scaled up to other compounds like benzene? Okay? You're not responsible for being able to draw out this structure, so don't stress about the structure. But this is the structure of benzene. How many of you think that would be an easy structure for you to predict and draw? Okay, cool. Good. Okay, so it's not an easy one for us to come up with. So what we might do is look at a chemical formula instead of the structure to kind of simplify what we would be doing as far as our calculations. So what would our chemical formula be? C6H6. Is that a fully reduced ratio? No. So what we might do is say, well, shouldn't we reduce that down to C1H1? Okay. For the molecular compound, it doesn't make sense to drop it all the way down to the empirical formula because we don't get a perfect repeating pattern that we get with our ionic compounds. Okay? It isn't carbon bonded to hydrogen and then just cycled and repeated out a whole bunch of times. If you notice, the carbons are bonded to each other, then to one hydrogen. Some of them are double, some of them are single. That structure doesn't make sense to boil into an empirical formula. Okay? Or into a reduced ratio. Okay? So it is a different kind of system than we've seen with the ionic compounds. Okay? That said, if I was to say study an organic compound or a molecular compound, covalent bonds, I might go through an analysis that allows me to figure out the reduced ratio, the amount of individual carbon atoms or hydrogen atoms with respect to each other. That would then be known as the empirical formula. Okay? So when we think about the use of empirical formulas, it's really important for covalent compounds, and really important is a weird statement, which we'll look at in a second too. It's important for our covalent compounds. Our ionic compounds, by definition, start at the empirical formula. Okay? Our covalent compounds, We could reference it as an empirical formula, or we could reference it as a molecular. And so depending on what we're trying to do or where that information came from, we might reference different pieces. Okay? And so what this section is now trying to do is say, well, how would I calculate an empirical formula? Where would this ultimately come from? Once I have an empirical formula, can I turn it into a molecular formula? What is the information I would need to facilitate me through that? Okay? So where these techniques are ultimately coming from is kind of old school chemistry. We didn't have a lot of fancy equipment to be able to analyze the structure of our compounds. Nowadays, we got a lot of fancy equipment that can analyze the structure of our compounds, and so the need to dig into an empirical formula becomes less and less important. Okay? So why do we then make you do it? Because we like watching you suffer? I don't know. Right? It does kind of get at some basic components of what the formula shows, so it is useful in that respect, and it can help tie and reinforce the meaning of a formula. Right? So let's go through and kind of take a look at that. To that end, because I think it is kind of an unnecessary skill set, okay, I tried to boil down empirical and molecular formulas, or how to discover them, into just bare minimum steps. So if you're being asked to discover an empirical formula, those are the steps you need to do. If you're being asked to convert into a molecular formula, those are the steps you need to do. Okay? If you follow those steps, you got your answer. If you don't follow those steps, you might have some trouble. Okay? So, in the empirical, our first step is to convert everything into moles for each of the elements. The next step will be to divide all the mole amounts by the smallest mole value that we calculated from number 1, okay, and then round everything off and multiply until we get whole numbers. Okay? That then sets it up with our empirical formula. Each element by the whole number. Okay? The molecular format, we determine the molar mass for our empirical formula, and then we'll compare that to the molar mass of our molecular formula. Once we know that, we now know the ratio by which we have to scale upwards from the empirical up to the molecular, and we just have to multiply everything through. Okay? When it says the number from 2, what is this 2 referring to? The step before it, step 2. So when we do that division, we're multiplying our empirical by the whole number found in step 2. Okay? So let's poke at this. An unknown compound of radium oxide. Right out of the gate, I screwed up. I kind of apologize for that. Why did I screw up with this? What can you tell me about radium oxide? It's an ionic compound. The whole point of empirical formulas is not ionic compounds. So it's a bit of a dumb example, but we're just going to power through the math without having to deal with any of the cheats on this. So an unknown compound is found to contain 0.726 moles of radium and 12.3 grams of oxygen. What is the empirical formula? Okay. Our empirical formula is our fully reduced ratio. So we would take radium and I would take oxygen, and I want to know how much radium and how much oxygen go into this. So X and, I meant to do color here, Y. Okay, what are X and Y? Well, what are the units on the X and Y? Moles, okay? Or atoms, either work, okay? Are atoms something we're likely to measure? No, so it probably makes sense to relate them as moles instead of atoms. Okay, so I can go back up to the question and say, am I given either of those pieces of information? So X is the moles of radium, Y equals the moles of oxygen. Am I given the moles of radium? Actually, it's right there. Okay, so I know X whoops, we color code. X is 0.726 moles radium. Cool. Am I given the moles of oxygen? No. Well, can my chemical formula, can that be in grams of oxygen? No, the chemical formula gives moles. That's the point of the chemical formula. Okay? So what am I going to need to do to that grams of oxygen? I need to convert it to moles. Right? So I will take my 12.3 grams of oxygen, and that needs to become moles of oxygen. Okay? Same problem we've been solving the whole semester. What do I want? Moles of oxygen. Where do I want it? In the numerator. So I'll put moles of oxygen. What do I have? Grams of oxygen. Is there a conversion factor that relates the moles of oxygen to the grams of oxygen? Yes, that conversion factor is found on the periodic table. And I get 16.0 grams of oxygen is 1 mole of oxygen. I can now punch this into the calculator and I get 0.768 moles of oxygen. Okay? So now I can take all of that information together, and I would say my chemical formula for radium is Ra 0.726 oxygen 0.768. Box it in and I'm done.
No.
Why not? Our point of the chemical formula is to get whole numbers. Okay? And it comes back to the units that we would associate from that chemical formula. Moles is the most relevant, but we can get to atoms. Does it make sense to have 0.726 atoms? No. Okay? So the number that has to be inserted into the formula has to make sense both with the number of atoms and the number of moles. That doesn't make sense with the number of atoms, so what I'm going to have to do is relate those two values in such a way that I can get them to whole numbers. How can I do that? I divide by the smallest amount of moles. Which one is the smallest amount? 0.726 moles of radium. This is going to give me 1, effectively, mole of radium. Okay, and I do the other one, 0.0726. What do I get? .768 divided by 0.726. 0.057. So now my formula becomes radium 1, oxygen 1.05. That's still not a whole number, but that's pretty damn close to 1. So I could say Ra1, O1. Do we need to conclude the ones? No? So what's my formula? Rao's pasta sauce. It's pretty good. Okay, and there we are. Make sense?
Why do you have to do the dividing thing? Can't you just round it to 1?
So you might say, well, couldn't we just round the 0.7 up to 1? Well, you're then making the statement because that's close to 1. That 0.7 could have been 72.6. Okay? So don't force the numbers in this situation just to match out. If it's 72.6, does that round to 1? No, you might as well round to 73, right? So RA 73, you'd still have to do the whole, you'd have to do the smallest whole number. The empirical formula is always that reduced ratio. Yes? So again, if we go back to what I said right before we started this solve, what did I say? This was a crap question because it's an ionic compound. Because it's an ionic compound, we could have predicted that formula from the outset. Yes. Okay? But I said we're going to power through and just do all the math anyway.
So if it was like copper oxide?
Copper oxide would have been a better example Copper oxide is still an ionic compound, but why is copper oxide a better example?
We don't know the charge.
You don't know the charge on the copper, so you wouldn't be able to just guess to the formula because you don't know the charge. Okay? So radium oxide was just a horrible choice all the way around.
Use it for like copper oxide.
You could use it for copper oxide, yeah. And we can still use it for radium oxide. It was just kind of a bit silly.
So it would be
We didn't have to.
What would be a perfect example for it then?
Okay? What would be a perfect example? When are we supposed to be using empirical formulas? For the non-ionic compounds, or covalent compounds. Just a sec. When do we have a covalent compound? Two nonmetals. So radium, metal, doesn't work. Copper, doesn't work, also a metal. Okay? So ideally we'd be applying this to our non-metal type situations. So could we do another example? Yes, absolutely. There it is. Your turn. Set it up. See what you can come up with for your empirical formula for this unknown compound. Opinion of me. So if we go through and take a look at this, okay, we're being asked for the empirical formula. Okay, what are the elements in our empirical formula? Carbon and hydrogen. So what we're being asked for is what is X and what is Y. The units on those can be either moles or atoms. It's up to you to decide which one you want to use with or work with. I would argue moles is easier to work with, but that is your choice. Okay? So what are we given as far as our moles of carbon? What are we given about carbon? We're given grams of carbon. And we're told, what, 24? Okay, what do I want? Moles of carbon. What do I have? Grams of carbon. Where do I find that conversion factor? Periodic table, 12 grams, 1 mole. Punch it into a calculator. For those of you that did sig figs, 12.01, would you give me a number?
2.
2.00. Oh, so it actually...
I got 1.9998.
Oh, 1.998.
Confusing because they only differ by 0.01. So it's very, do you want us to round?
So officially, when should you round?
At the end of the question.
The end of all of your calculations. So you shouldn't be rounding yet. Okay? Shouldn't be. Yes, it's all going to come out to be the same thing. It's not going to matter in this case. Okay? What are we given for our hydrogen?
2 grams.
We want moles of hydrogen, 2 grams of hydrogen. Every time I do this, so we'll share this with everybody and even record it out into the video, every time I go through and do this, I see the question, I go, I hope nobody asked the question, and somebody asked the question, is that moles of hydrogen as the element, or is that moles of hydrogen as the atom? Because when should it be moles of hydrogen as the atom? When it says it. Did it say it? No. So that's kind of a vague question. That was horribly written on my part, and I apologize. Because I knew what the answer was, quickly edited it to atoms. Okay? Which means the symbol we're looking at is H, not H2. So where do we find the relationship between the grams and moles for hydrogen? That's our periodic table. 1.01 grams of hydrogen is 1 mole of hydrogen. The number we get?
1.980.
982? Moles of hydrogen. Okay. Those aren't whole numbers. Okay. So, oh man, and of course she walked out because the initial question we had earlier is couldn't we have just rounded up? So then that would be C2H2. And we said, well, that's the empirical formula. No, that's not the reduced ratio. This is why you should always go through and do the reduced ratio first. Which number is smaller? The numbers are so similar, it's actually confusing me. Is it this one?
Yeah.
So we divide both by that, 1.980. What do we get? 2 point... Shh. 1 point...
Yeah.
I was like, whoa, okay, we did something wrong. 1.080, like 2.
2, okay. And the other one for sure comes out as 1. Okay, what does that then mean? I'm going to get C1H1, which I could then go through and say was CH. And there's my empirical formula. Kind of make sense? Right? So really all we're doing within this is just saying, well, what the hell do those subscripts mean? Right? Well, what have we done the whole rest of the semester? Addressed what those subscripts meant. Okay? So now all we're doing is using that as a calculation in a theoretical kind of lab system. Make sense? Okay? There are other ways it could be formatted. Let's see, not that one yet. Okay? Because if we go back and look at where we started with our directions, if we're given grams, what do? You convert into moles. That's what we were done. It could be presented as percent composition. Okay? So what you'll do is assume a 100-gram sample. Okay, so if I told you it was 20% carbon and 80% hydrogen, what does that mean? Well, I can't do a gram to mole conversion. What if I assume a 100-gram sample? How much of it is carbon?
80 grams. Or is it?
It'd be, I think I said 20% carbon. So it's now 20 grams of carbon and 80 grams of hydrogen. Now I have gram amounts. Now I can convert to moles. Okay, so it becomes easiest if you see those percent compositions to just immediately assume 100. The percents become grams, and you can just go through and do your conversion. Make sense? Okay. So let's move to our empirical to molecular formula. So our empirical formula was the smallest whole number. The molecular is the actual whole number ratio. So if we went through and looked at this question, you might be like, well, didn't we just solve this?
Yes, but no.
Yes. Well, actually, no, it just says the empirical formula. So we literally just solved that, so let's change it. A small amount of the same sample that we just tested, okay, was found to have a molecular mass of 78 grams per mole. What is this compound's molecular formula? So we just tested it and determined the empirical formula to be what? Okay, sorry, I'm trying to catch up. The empirical formula we tested decided was CH or C1H1. Okay. What we're being asked for is what is the molecular formula. Okay, well that molecular formula is now CXH. Why X?
I don't know.
If we go back to our empirical formula, the molecular formula is just a scale up of the empirical formula. If I know my empirical formula is C1H1, if it's CX, H must be X as well, because I know it's a 1-to-1 ratio. So it shouldn't be XY. In this case, it should be XX. Does that make sense?
Yeah.
Okay. So how do I figure out what X is?
From what you've given into your actual molecular amounts.
Okay, what do you mean?
So you've got to take your 78 grams per moles and then take that into conversion. Find out from the ratio.
What are you converting? What's your conversion?
Like what am I finding?
Sure, I can accept that too. What is it? What are we setting this equal to?
Well, you're going to have to do two of them. So one's going to be carbon. And
Okay.
one's gonna be hydrogen.
So this will be moles of carbon.
Yeah. And then you're going to find your conversion factor.
What conversion factor?
To go from grams to moles.
For what? And arguably, don't I have grams to moles?
Yeah, but you want to get moles on top.
Okay, moles of what on top? Could say moles of carbon.
Carbon XH. Or no, not
So I would also need to get rid of moles of that. How could I get rid of those? Do I have a relationship between the amount of carbon in this formula? Do I know how much carbon is there? No. So do I know a number that I'd be able to relate in there? No. So it doesn't quite work. Maybe you're thinking of something else that I'm not translating nicely, which is
Probably not.
easily possible. Okay, there's kind of a brute force way. Do we know the molecular mass for the CXHX? Yeah, it tells you. It tells you it's 78 grams per mole. Do you know the molecular mass for the empirical formula? How do you find out? Someone shouted out the number. Where'd you get the number from?
Was C1H1, so you just take carbon's molar mass plus hydrogen's molar mass, which gives you 13.0.
There's 1 carbon, 1 hydrogen. I know the molar mass for each carbon and hydrogen. I know that's 13 grams per mole, right? I tell you not to do the slash, so I better not do it too.
Wouldn't you just divide by the empirical formula? The mass of the empirical formula?
If we follow the direct calculation that I tell you to do in those previous slides, what does it tell you to do? Take the 78, our molecular formula mass, and divide it by the empirical formula mass. What does that get? Carry the 3, I believe that's 6. Wow. It's like I've done this. Okay. What does that mean?
Those are the subscripts for the molecular formula.
I now take this number and I multiply it by my empirical formula, which means my empirical formula becomes C6H6. Didn't we just talk about that compound?
Did you also talk about benzene?
Yeah, this was benzene. Yeah, we just did this. Okay, so we now take it back to benzene. That's the exact process behind this. Okay? If you don't see that 78 divided by 13, you can try the other way. Well, what if it's 2 of each? What would my mass be? 13 times 2. 26. Is that 78? Nope, so that must be wrong. So let's try 3 of each. Let's try 4 of each. You can brute force it, but
That'd be much easier.
you could just do the math to get that relationship. Does that make sense? Okay? And that's really all you're being expected to do, is to recognize that it's just a scale up. Okay? Some of that scale up becomes tricky. If we go back through and look at stuff that you were explicitly given, okay? You're explicitly given that. You're explicitly given this. Whoops. Okay? What are you expected to recognize and determine? Well, what's your molecular formula and the molar mass for the empirical formula? Both of those things are things that you should be kind of interpreting out of the question. And as soon as you've done that, it's now just a ratio scale up.
Will we always be given the empirical formula or the molar mass of the... or will we
Yes.
oh.
Yes. Yeah. To solve for the molecular formula, you need to know the molar mass, okay, of that compound. You would also need to know the empirical formula, or at very least the empirical's molar mass. Yes?
Now, if that number is divided by the molecular formula, that's 6, what if that doesn't divide? Do you round up or down?
So if it doesn't divide nicely, it's probably because you did some math mistake somewhere. That's going to be the first statement that I would make, because at least for this class, we're trying to put those as nicely and neatly as possible. In a real lab situation, they probably aren't going to come out nicely, okay, which means there's probably an experimental error. How would you minimize that experimental error? What's that?
Don't make any errors.
Bigger sample size.
You could repeat the measurement with a different sample size. And then you could start to make comparisons of what you got from each of those things and average out your results. So when we're trying to use these things to come up with actual values, we don't run one experiment. We run at least 3 so that we can average those results to get closer to the truth. Okay? Or we would improve the instruments we're using to make those measurements.
So this is supposed to scale up? Like, it should always be a whole number because
It should, It should always be a whole number, and I'm going to attempt to wing an example, which I will probably botch the hell out of. But I'm going to attempt to wing an example here in a second to see what that would mean if we could get a different result. Okay? Does that kind of make sense? So for right now, you should be getting whole numbers. When you test it in the book, you will get some not whole numbers, and that's what I'm going to attempt to do correctly. Maybe that one, because it didn't come out perfectly. That should have come out perfectly. Yeah, I think that one comes out perfectly all the way through. Yeah, that one's going to come out perfectly all the way through. So, are we done with what's up there? And let's see if Mike can create something off the fly that maybe works.
Will there ever be like a CX each Y where they have different numbers?
Yeah. Okay. So the X for the hydrogen and the carbon, that ratio doesn't have to be 1-to-1. It could be anything. Okay. As long as it comes out to be a whole number. And so that's what I'm going to attempt to do here. So we'll try it with this. Grams of carbon. In our sample, we found that carbon came in at, I think this will work. I think I got this. I found in my sample that I had 24 grams of carbon, and I had grams of hydrogen was 3. So start working on that to give me an empirical formula. While you're doing the empirical formula, I'm going to try and do the math to get a molecular formula. First help me. 6 times 12 is 60? 50. 72. Sorry. Are you laughing at me? So yes, that's what you're saying. You're laughing at me. I can pull this off. So you are given a sample. That sample is found to have 24 grams of carbon, 3 grams of hydrogen. What is its empirical formula? That same sample, we found that it has a molecular formula mass of 81 grams per mole. What is the molecular formula for the compound? Make sense? Okay. Try and get through it. I'll come around if you got questions on it, and then we'll go through and see. Which is okay. That's kind of the point of this example. So in our empirical formula, what we're trying to get into is moles. Okay, so pretty universally, we saw grams carbon, moles carbon, 12. This gets us 2. For those of you that want to deal with sig figs or proper units, let's deal with the proper units first. Okay. For those of you who want to deal with sig figs, that's okay. You can go through and push the sig figs a little bit. It's not going to really change the numbers much. Okay. 1 mole of hydrogen. Man, no, I had that right. 1 mole of hydrogen. 1 gram of effing hydrogen. Yeah. Which would be 3 moles of hydrogen. Okay. What was the next step? Divide both of them by
2.
The smallest number, which would be 2. And so for carbon, I would get 1. For hydrogen, I would get 1.5. So if I looked at my formula, it would be carbon 1, hydrogen 1.5. I can't have half of a hydrogen atom. Okay? So when we talk about coming out to whole numbers, for the most part, they will come out to whole numbers because it's fundamental chemistry. Okay? In a more advanced chemistry class, they may not come out to whole numbers. For sure, this as a practice problem does pop up in the textbook. They do have it come out as a half value. Okay? So whole numbers, close to whole numbers, you can round. This isn't close to a whole number. In fact, that's dead in the middle. In fact, that would be halfway between 2 things. What could we do? we could multiply it by 2. If I multiplied that by 2, this becomes hydrogen 3. So C1, hydrogen 3? No. If I'm multiplying the hydrogen by 2, I also have to multiply the carbon by 2, and I get, stupid eraser. C2H3. You get a stupid eraser whenever you solve. Yes.
So why did you divide by 2 in the first place?
So we divided by 2 in the first place, and so what you might have said, well, is why don't you just do 2, 3 right there? The only reason it came out cleanly at 2 and 3 is because I tried to do all the math in my head, and I'm not good at math, so I had to pick easy numbers that were nice and round. Okay, that's literally the only reason those numbers came out nicely. Okay, so we always need to divide by the smallest whole number and get used to that as a process. Okay, that establishes this weird fraction. We fix that weird fraction by multiplying out by 2. This 2 and 3 from the solve here is literally only because my brain is that bad. Okay, if other people have better brains, they can do and we already proved how bad it was with a 6 times 12, right? Thank you for laughing at me. Okay, so I could only come up with those numbers because I wanted this ratio. I knew I wanted that half, and I couldn't come up with fancier math to get that ratio to come out right in my head. Does that make sense? Okay, so that now gets me an empirical formula. How do I get my molecular formula? I find the molar mass for my empirical formula, which if I did this right, it's looking like I screwed this up too. Damn it. Carbon is 12, but there's 2 of
So
them.
it's 24.
24. Hydrogen.
3 hydrogens times.
So we've got
So 27.
27. Actually, I think I did do this right. Did I do this right?
Yeah.
Yeah? Cool, look at that. So I would take 81 divided by 27, and I get? I should get 3 cleanly, which means my multiply those both by 3, and I'm running out of space, so we'll go to the upper left-hand corner. Okay, for those of you complaining about my directionality on the board, sorry, we're all over the place. We multiply everything by 3, and I get C6H9. There's my final molecular formula. Yes?
So, remember on the question before you put the molecular formula is CXHX?
I just didn't show that work. Okay, it is, and so in that case, on the previous one, we had CXHX, right? Is this one CXHX?
No.
No, this is going to be XY. How do we know it's XY and not XX?
They're 2 different numbers.
Those 2 numbers are different. Okay, so we would know that right out of the gate that those are 2 different numbers. Okay? Kind of makes sense?
Wait. Where'd you get the 81?
81, I had to give that to you. That was some of the given information. So if we kind of do green, given information, given information, given information.
Oh, now I see. Okay.
Does that work? Yeah, this is what happens when you ask me to make up a question on the fly. This is why you shouldn't ask me that. Make sense? Okay. I believe, almost. Okay, we get the summary of the rules again on how you go through and do the empirical and molecular formula. It looks to me like the majority of you had that nailed pretty well.
Yeah.
So that's kind of cool. I like that. That makes me happy. Which kind of puts us in review. Do you want to take 5 minutes to write what new content you think you've got for this exam? What areas you've got trouble with, that kind of stuff? Do you want to spend time trying to come up with that now? Yeah? Okay. Spend a couple minutes. Try and reflect back on those ideas. Write down what you think is new content areas. So based off of what we talked about since exam 2, what do you think is new? That you're like, I need to remember this. Okay? Or I need to go back and look at this as being new stuff. Okay? What are you currently having troubles with? So think back to all that stuff. Maybe the stuff you're having trouble with was from past exams, from past units. That's fine. But reflect back on that. What do you feel super confident on? You're like, this is easy. I don't need to see any more of this. Stop talking about this. and then if you have specific questions. Okay? I'm not going to collect it. I just want you to think about it, write it down. Okay? And then we'll kind of share out in a second here, wouldn't it? If I attempt to kind of guess out where those chapters are, density is chapter 2. Temperature, I think, is chapter 2. Heat and specific heat are chapter 3. The energy laws, I'm almost positive, are chapter 3. Okay. These two are 8. This is 9. This is 13. These are 10. And I think all of these are 9. Okay? So the majority of our time is spent in conversions. This is a difficult question or exam for me personally to write because we spent so much time on conversions. Okay? That means every question is a question about conversions where you would have to go through and solve math. I think that's a bit excessive. Okay? So I could be like, well, I'll just do less questions. Less questions means
They're worth more.
each question's worth more. If you get it wrong, that hurts. Okay? So this is an exam where I'm at a struggle to get 40 questions that doesn't make 40 questions full of conversions. Okay? So reviewing the practice exam is a really, really good idea. Okay? Because I'm already at a loss to come up with questions, which means I'm going to probably pull from the only sources I've got. Okay? Kind of makes sense?
Gases, 2 gases.
Sorry, what's that? What about gases?
SS, yes, isn't it 2 gases? Don't you teach English? Like,
These are the questions we need to answer.
No. That's got to be 1S. Well, that's cool. So within our gas, and the gases one is this weird kind of gray area one because it's sort of on our competencies and sort of not really. Okay. So it's there. You got to watch out for it.
actual question, are you going to test this on Pivnert as well as I have been exam?
So Pivnert shows up, but remember the context of how I said it shows up. Okay. Pivnert is more the relationship between those. Okay. Not just here's all these things, plug it in and solve. Okay. So if the pressure doubles, then what would happen to the moles if the volume and temperature remained constant? The moles would have had to go up by 2. Okay? So it's recognizing the relationships between those. I think if you have Pivnert, the relationships are there, and it's just a question of looking at Pivnert to evaluate that. Okay? You don't have to do that. You could just be like, well, if everything else stayed constant, then the moles have to go up. So some of those relationships are easier to nail down than others.
But you're not going to have that many calculations with the...
And I would argue the extent of the calculations will be in this double, triple kind of thing. I'm fairly confident that I would not give you a question, what is the volume if pressure is this, moles is this, and temperature is this?
Okay.
Right. I can't be 100% on that, but I think that's a dumb question to ask.
So you're just going to keep it as ATM and...
Yep, and I said we're not doing pressure conversions, so you don't need to stress about those. Ultimately, again, pressure conversions are just a conversion. I would have to give you that conversion factor. You would just have to use it. What value do I see in that? None, so what would I ask? So really when we're looking at gases, you're looking at those relationships, what happens to the pressure, what happens to the moles. How would this look graphically? Okay? And then dealing with the conversion factor moles to liters at STP. Remember I soapboxed a lot about that stupid conversion? Right? You might see a question or two about that concept.
40.
Okay. Yeah, I don't know. I would go all 40. Okay. But you will probably see some questions that really harp on that aspect.
So regarding molarity is when it has like 3m for a solution, does that mean there's 3 moles per 1 liter solution?
So when we look at the molarity, if we say 3 capital M, That is the same thing as saying 3 moles of your substance in 1 liter of the solution.
Okay.
So the 3, or your number will go with the moles.
Also, I just checked because, so the imperial formula and molecular formula stuff is chapter 8. And then the limit
Oh, is it?
and the
Damn it.
percent yield are chapter 9.
Anybody want to make some snarky comment about my reading ability?
I did look it up. Gas with 2 S's is a verb.
I said it looked wrong. I saw it over there.
Is a verb?
Like someone gasses up their cars with 2 S's, gases as in
Yeah,
Oh.
that's a noun.
Interesting.
just in case you were.
Oh. So you were right. It still looked really horrible, but
No,
but in this context, it was wrong.
You used it right.
I used it right, yeah.
But it does exist also, 2 S's.
Okay. Other questions? You're right. Yes, there would be 3 S's technically. Conversion factors. Again, we've got this kind of summary slide. I think this would be helpful as well. Personally, I think this has it right there. It's got the pieces that you need for what those conversion factors are and kind of addresses them all kind of neatly. You'll notice also I have more appropriately used the word objects. I think that is from past classes and I haven't fixed that. I believe on the tests, if it's something like that, or even with Sagan's, if you look at the practice exam, you're like, what the hell, how do you solve Sagan's? You solve it the exact same way you solve every other friggin' question. It's not any different. Okay? Objects versus things. Okay? Do you guys have a preference?
Things.
Prefer things?
Yeah.
Things just sounds better.
Just because they already showed up in the,
What's that?
just because they already showed up in the PowerPoints as things.
Yeah, okay. I will try and make sure that that shows up as things on the test.
As far as what we're given on that page where we have all the information that we're given, do we have to still have like yards and everything on there? But what will be on there?
So the given information, I have not touched since I built it for the exam 3, however long ago when I first built
So
exam
it'll be
3.
the same as everything
So
else?
it's the same. If you look exam 1 to exam 2 to exam 3, the exact same stuff is given to you throughout the entire semester. Exam 2 had all that on it too.
No, it was exam on Tuesday.
The exam, no, it's next Thursday. So next Tuesday will be a review day. That's going to be where you come in with questions. If you're like, I got this, then you don't need me. That's cool. A little sad, but.
That just means you're a good teacher.
We won't go that far. There was a question? Yes.
So, when you say objects and things, it's talking about atoms or molecules.
So in chemistry, what are our things or objects? Atoms, molecules.
That's it.
Okay, those are our things. Okay.
You could have a mole of eggs.
But are there other contexts that you would be asked to use? I could ask you for a mole of eggs. Okay.
Can I do that?
Eggs are still an object or a thing. You should still be able to use that. Okay. The harder part is recognizing that it's still tied. Our chemistry is that they're things, not measurements.
But couldn't you have like moles of grams of something? Maybe a ton.
So, and this is where it gets weird. Okay, so we'll address this one again. Can I have moles of grams?
No.
Yes, but what I'm referencing is not the measurement. What I'm referencing is the physical object that is a gram. Okay? And the problem with that is that people then try and use it as a measurement conversion. You can't use it as a measurement conversion. It's a physical object. And that's why I would just avoid using grams. That's the problem with the English language is we have the measurement and then we also have the physical object that is a gram. Yeah, I haven't looked at it to figure out the weight of planets and all that, but it's big. Okay. Other questions? Hi. So there's that summary slide. You have a question?
18 years of chemistry, this is where we're at. Or 1800 years.
800 years is where we're going with that. And no, we're actually a hell of a lot further along.
Oh, we are?
But did you really want to learn about all of that? Okay. In addition to all of this.
If it
No.
wasn't for a grade.
And so that's where I think a lot of people then kind of say, we're going to do a little bit of skipping here, so you may not want to watch. Oh, Jiminy, it's way back there.
Also, why is English so good?
Why is the word so, what?
I said, why is English so good?
Whoop, there we go. That's what I wanted.
It's an amalgamation of like several different.
Yeah. I would argue English isn't broken. It's just taken the best and worst parts of all of our other languages. Okay, so setting up this question, because I got a lot of people asking this, because this showed up as the kind of extra credit on the previous exam. Okay, you should be able to go through and solve this one all the way through. So let's look at some kind of basic structural aspects behind this. What are you being asked to solve for? The molarity of nitric acid, which would be a capital M of nitric acid being HNO3. Okay, capital M we know to be moles over liters
1 liter, right?
of our solution. The numerical value we're trying to solve for. Okay, so we don't know the numerical value yet.
So the amount of liters can change. It's not amount of moles per 1 liter.
In your final answer of what a molarity is, it will be per 1 liter. The issue that I have with you saying 1 liter is that you're now going to go and put a 1 here or a 1 liter of solution over here, both of which are questionable statements to be making. Okay, so let the number come to you from the calculation over here. Okay, so if that's what we're trying to solve for, we now need to come up with some way to deal with this. Okay, what is our given information?
745 milliliters.
Milliliters of what?
The acid.
Of the nitric acid solution. So that would really be our acid solution. Okay? And because we've got that distinguishing, we might go over here and say, well, this is actually our acid solution. Okay, what else are we given?
0.02.
Molarity, which we immediately convert into moles of barium hydroxide. Note, I'm immediately going into a chemical formula. Okay, and this would be liters of?
Acid solution.
This is not acid solution anymore, because what is the barium hydroxide acting as? It's acting as a thing that reacts with acids. What reacts with acids? Base solution. Okay. What else am I given?
I don't know what's the solution.
What's that?
Oh, okay. That makes sense.
Because it's, dissolved in molarity. And what's our last piece of given information?
165 milliliters of barium hydroxide.
Right? And really, that's our barium hydroxide solution, which is really our base solution. Okay? So now it's a question of how can we incorporate this information back up into this system. Okay? Well, do we see anything that stands out? Okay, so we get a call out for the 0.200 moles of barium hydroxide. Why did you pick that as a call out?
It's both molarity.
So they're both molarities, so that could be reasonable. Is it the same substance? No, but if you're going to say it's both molarities, what we could go through and do is attempt to put that conversion factor in. Do we know if we should place it as is, moles of barium over the liters of solution? Okay. Well, it's supposed to match the molarity at the end. Maybe that makes sense. So if we don't really know, as long as we acknowledge that we don't know, what could we do? We put it in and we just start working with it. We now have something to base everything around. If at the end of that calculation our units don't align, what happened? We made the wrong assumption for the insertion of that, and what do we have to do? Flip it over, and now we do set it all back together. Does that make sense? As long as you know that initial assumption is either a guess or has some really solid evidence behind it, you're fine. You just have to acknowledge that. Okay? So in this case, the suggestion was made that we want moles of barium hydroxide over the liters of our base solution. Okay? We now have a place to start. Are those equal to each other? No. So what do you need to do?
Substance conversion.
You now start needing to do some conversions. Okay? So another suggestion was made that we need a substance conversion. I don't want barium hydroxide. What do I want? Nitric acid. Where do I find a substance conversion?
Balanced chemical
From a balanced chemical equation. What units are from a balanced chemical equation?
moles.
Moles. I don't know what those numbers are. Okay, so don't start forcing numbers in. Write the units first. I know that is come from a balanced chemical equation, so what could I do now?
Make a balanced chemical equation.
Write out a balanced chemical equation. Are we told what the products are?
No.
No, so what do you have to do?
Know the type of reaction.
You have to figure it out by knowing the type of reaction, by matching that to the patterns that we've talked about in the past to be able to predict those. Okay? I have no problems continuing to do this right now, but I'm going to suggest that we hold off, and if we want to talk about it on Tuesday, we absolutely can and can push through the rest of it. But right now, we are done with class, so if you got to take off, you got to take off.